Hi class, welcome back. I want to wrap up part 4 of this course. Been talking about the uniform plane wave um, as it propagates in free space. And we've developed the equations for that, but now we want to extend that just a little bit further and talk about um, power density and energy storage related to those waves. First, I want to look at a historical background. This individual was educated at Owens College, which is now the University of Manchester, and Cambridge University. In his work, he worked at Cavendish Laboratory with James Clerk Maxwell, so he was a contemporary of Maxwell. This is an image of this individual. Maybe you can guess who it is. If not, it's John Henry Poynting. So it was appropriate we look at him. We're going to be talking about the Poynting Vector here in just a little bit. Some notable things. He developed the Poynting Vector and the Poynting Theorem dealing with electromagnetic energy conservation. He performed a measurement of Newton's gravitational constant by innovation means in 1893, so he got a very accurate measurement of that. Then he was the first to realize that the sun's radiation can draw small particles to it, almost like static electricity effect. So again, we're wrapping up part 4, this wave propagation in free space. I wanted to define and talk about the Poynting vector and energy storage. So having now derived expressions for the EM field generated by an infinite current plane, the current plane in the XY plane, we'll now take a closer look at the source that is required to generate this plane, this current source in that plane. So in general, the current of the source is flowing against the force due to the electric field. So we've got some things kind of working against each other here. So this means that a certain amount of work must be done by the source to maintain this current flow in the sheet. So we'll again consider a rectangular area, this delta x and delta y, on the current sheet. So we've got this area defined here. Let me get my laser pointer going. So this area here is delta x and delta y on the current sheet. So then the charge then crossing this width delta y, so it's up here. Remember, the charge is going up and down, so it's going to go across this line here, this delta y. In time delta t is then defined by this. So we've got this change in charge is equal to the current density times this delta y, this length, cosine omega t delta t. So as the charge changes with respect to time. So the force then exerted on this differential charge is then defined by our equation. Remember, we had F is equal to the charge times the electric field. Well, we've got an expression for this differential charge. We plug that in and we get this expression here of the magnitude of the current density times our width times this driving function for the current density with respect to t times this electric field Ex in the x direction. This means that work then is required to be done against the electric field in displacing this charge in the current sheet by this distance delta x. So we can express this as follows then. So this amount of work, differential work then, is this force over this differential distance. And so when we plug the values in for that, we have a value for the f of x. We plug that in from before, put in the delta x and the delta y. So this means then that the power that must be supplied by the source to maintain the current sheet over the area can be defined then as the time derivative then of this original expression. So we divide by the dt, so this is the change in work over time, which is the definition of power. So we have this expression for that. So then if we recall then that our electric field on the sheet is defined by this term here, which is just the intrinsic impedance times our current density definition, we now have this new expression, intrinsic impedance times the square of the current density divided by 2 times our differential rectangle on the current sheet. If we now consider again the box formed by our differential lengths, delta x and delta y, and then this third dimension being either side almost touching the xy plane, we can recall then that the power flow out of the box is defined by this integral that we used last time, crossing our electric field with our magnetic field, taking that cross product. So as follows, when we plug in the values here, we get this expression here, what we had for our electric field in the z direction, and then that's going to be dotted with this delta x, delta y, or our rectangle in the z direction. And so when we work all that out and do the calculus and combine some terms, we get this new resulting term here. So this is exactly equal to the power supplied by the source. If you look back at one slide, this is the exact same expression that we got for that. So the meaning then of this vector E cross H, or electric field crosses magnetic field, is that this new vector is the power flow density vector, which can be used to determine the total power flow over, or maybe better be thought of out of, a surface, as we've just seen. So this vector then is known as the Poynting vector, and we denote it by the vector P, or the boldface P. And so this is just expressed then as Poynting vector is equal to the electric field crossed with the magnetic field. So that now the power flow out of this closed surface S, we can say, is defined as the integral over this closed surface E cross H. So this is our power flow of our propagating electromagnetic wave. Very important. So now we want to turn to our hypothetical example, and considering this region again in the positive z direction, the magnitude of the newly defined Poynting vector then is given by this expression here. And so this Poynting vector in the z direction, which is our E in the x, our electric field in the x direction, and magnetic field in the y direction. So we now have this new expression here for that. So the variation of this Poynting vector with the position for some arbitrary time, I'll just say time t equals 0, which gives us this first wave here, can be shown as this. So our Poynting vector is going to vary with position. So if we now consider a box then between this arbitrary position z and then z plus delta z, and having the same dimensions in the xy plane of delta x, delta y, we would in general attain a result for the power flowing out of this box. So we can create this box between these 2 points here. So this implies that there must be some energy stored in the volume of this box to make power flow. So this is a very important concept, and this demonstrates that energy is stored here. But where does this energy reside? Where is it stored? Well, the only explanation can be that it must reside in the electric and magnetic fields. So this is showing us mathematically that these fields store electricity, or store energy. To better understand this, then we'll look at the power flow out of our box below. So we have this integral of Poynting vector over the surface, and so we have the Poynting vector at z, and then of z evaluated at z plus delta z and at z, so the difference in those two guys. And so when we take that, do some rearranging of the variables, we can see that it's just the partial differential of p with respect to z times delta v. So if we now replace this Poynting vector with what is defined as the product of our electric and magnetic field, and using some previous definitions, we now see that this can be rearranged and expressed as the partial with respect to position of our electric and magnetic fields, delta V. And so we take those derivatives by parts and plug that back in, and then we see we can now make the constitutive change between these two. And when we do that, we now come out to this new expression. Again, just following the math, working this out. We now come to the final, what we're looking for, and that is the derivative with respect to time of this product minus the derivative with respect to time of this product. So where this is known as Poynting's theorem. And so here we have an expression just in terms of the magnetic field. Here we have an expression just in terms of the electric field. But what in the world does this mean? So again, bringing this solution forward, Poynting's theorem tells us that the power flow out of the box is equal to the sum of the time rates of decrease of these quantities in parentheses. So as this decreases over time and this decreases over time, that's defining our power flow. Well, for this to translate into power, that is the change of energy over time, we know this from physics, then by definition, the quantities in the parentheses must represent energy, and that's going to be stored energy in the electric and magnetic waves in the volume of the box. So this was a huge discovery Poynting was able to make, and this is what helped us not only tell us there was energy in these electric and magnetic waves, it also quantified what that energy was. And so from this we can define now a more general quantity of the energy density in each of the waves as follows. So this is the major contribution Poynting made in electromagnetics, is we can now define these energies that's stored in the electric and magnetic waves.